All facts below are grounded in the same real, sourced fact set as before. NASA, University of Oxford, Harrison-Nichols team, Nature Astronomy, March 2026. This version keeps every specific claim about L9859d tied to that fact set, while expanding the general background, analogies, and explanations to reach the requested length. Nothing about the planet itself is invented. The added length comes from deeper, plain language explanation of the science around it. Picture a planet that has been quietly cooking for almost 5 billion years. It should have gone cold by now. It should look like every other small, rocky world we've found. It doesn't. Instead, it's still burning from the inside out, sealed under a sky that smells like rotten eggs, hiding an ocean that isn't made of water. It's made of fire. Scientists just built a 5 billion year timeline of this planet's life, and what they found doesn't match anything else we've ever seen. Today, we're going to walk through exactly what's happening on this world, why it's breaking the rulebook scientists use to sort planets, and why some researchers are calling it something entirely new. Before we go further, here's a question for you. This planet is being kept molten by sulfur trapped deep inside it, cycling in and out of its atmosphere for billions of years. Tell me in the comments, do you think that cycle ever runs out, or could a planet like this stay half melted forever? I want to see your theories down there. Finding a planet outside our solar system is hard. These worlds are so far away and so dim compared to their stars that for a long time, astronomers could only guess at what they were made of. A star is like a lighthouse standing next to a firefly. From here on Earth, that firefly is almost impossible to see directly. So instead of looking straight at these planets, scientists had to get clever. From the mid-1990s up through about 2022, most of the work in this field was simply finding these planets in the first place. One popular method is called the transit method. Imagine watching a lighthouse from far away, and every so often, its light dims just slightly for a few hours, then brightens back up. That dimming happens because something is passing in front of it, blocking a tiny bit of the light. When astronomers see a star's brightness dip on a regular schedule, they know a planet is orbiting it, crossing in front of the star's face each time it circles around. From how much the light dims and how often it happens, scientists can work out how big the planet is and how long its year lasts. Another method, called the radial velocity method, works a little differently. A planet's gravity gives its star a tiny tug as it orbits, causing the star to wobble ever so slightly. That wobble stretches and squeezes the star's light in a detectable way, kind of like how an ambulance siren sounds different as it drives toward you versus away from you. By measuring that wobble, scientists can estimate how heavy the planet is. Put those two numbers together, size and weight, and you can calculate something called density. Density is basically a measure of how tightly packed the material in an object is. But even with both size and weight known, all of this only got us so far. It told us a lot about a planet's basic shape and mass, but it didn't tell us what the planet's air was actually made of, or what might be happening underneath its surface. For that, scientists needed something much more powerful. Everything changed when the James Webb Space Telescope, or JWST, launched in 2022. Think of JWST as a giant, heat-sensing eye parked about 1 million miles from Earth, far past the orbit of the Moon, cold enough and sharp enough to pick apart the faint light passing through a distant planet's atmosphere. When a planet crosses, in front of its star, a sliver of starlight passes directly through the planet's air on its way to us. Different gases in that atmosphere soak up different colors of light, leaving behind a kind of chemical fingerprint in the starlight that reaches Webb's instruments. For the first time, astronomers could start reading those fingerprints in real detail, figuring out not just how big and heavy a planet is, but what its atmosphere is actually made of. That's exactly the kind of tool it took to catch what was happening on L9859d. It's worth pausing here to appreciate just how far this field has come in a short amount of time. Only a few decades ago, we didn't know for certain that any planets existed outside our own solar system at all. The first confirmed detections of planets orbiting other sun-like stars came in the mid-1990s. And for years afterward, each new discovery was treated as a major event on its own. Then space telescopes like Kepler came along in the 2000s and 2010s, staring at one patch of sky for years at a time, watching tens of thousands of stars all at once for those tiny transit dips we talked about earlier. That mission alone helped confirm thousands of new worlds, and it taught scientists something important. Planets are common. Almost every star you can see in the night sky likely has at least one planet orbiting it. What Kepler and similar missions couldn't do, though, was tell us much about what those planets were actually like up close. They were planet finders, not planet describers. JWST flipped that script. Instead of just detecting planets, it let scientists start describing them layer by layer. And L9859D ended up being one of the systems worth that kind of close attention. L9859d circles a small, cool red star about 35 light years from Earth. A light year is the distance light travels in one full year, moving at about 186,000 miles every second. So 35 light years sounds enormous, and it is, but in the scale of our galaxy, it's practically next door. Our galaxy stretches across roughly 100,000 light years, so a planet 35 light years away is one of our closer cosmic neighbors. L9859d is part of a small family of planets orbiting that same red star, and for years, scientists suspected this particular one might be interesting. They just didn't know how interesting. Red dwarf stars like this one are actually the most common type of star in our entire galaxy, making up a large majority of all stars out there, even though none of them are bright enough to see with the naked eye from Earth without a telescope. They're smaller, cooler, and dimmer than our own sun, which sounds like it might make them less interesting to study, but it actually works in scientists' favor in one important way. Because these stars are so much dimmer, a planet passing in front of one blocks out a comparatively larger share of the total light, making the transit dip easier to detect and measure precisely. That's part of why systems like this one, built around small red stars, have become such valuable targets for telescopes like JWST. It's not that the planets themselves are unusual for orbiting a red dwarf. It's that the dim light of the star makes it easier for astronomers to tease out faint details like the presence of hydrogen sulfide that might get lost in the glare of a brighter sun-like star. First finding, a planet that's too light for its size. Here's where the story starts to get strange. L9859d is about 1.6 times the size of Earth. Picture something roughly like Earth, but a bit puffier, like a basketball sitting next to a slightly bigger, slightly softer ball. If this planet were made of the same mix of rock and metal as Earth, scientists could predict roughly how heavy it should be, just from its size, the same way you could guess the weight of a bowling ball just by knowing it's made of dense, solid material. It isn't that heavy. Its density is unusually low for a planet that size, which is a scientist's way of saying there's less stuff packed into it than you'd expect. Imagine picking up two rocks that look exactly the same size, but one is surprisingly light in your hand. Your brain immediately knows something is different about what's inside it. Maybe it's hollow, maybe it's made of a lighter material, maybe there's gas trapped inside. That's the kind of mismatch researchers were staring at with L9859d. Something inside this planet isn't behaving like ordinary solid rock. This matters because density is one of the first and most powerful clues scientists have about what a planet is actually made of. A very dense small planet is probably mostly metal and rock, like Mercury. A puffier, lower density planet might have a thick layer of gas wrapped around it, or possibly, in some cases, a very different internal structure. Than anything close to home, that single clue, a planet lighter than it should be, or is often the first thread that unravels a much bigger mystery, and this time was no different. To put this in perspective, think about the range of densities we already know exist in our own solar system. Earth is one of the densest planets around, packed tightly with iron, nickel, and rock. Saturn, on the other hand, is famously so low in density that if you somehow found a bathtub big enough, it would float in water. Most rocky exoplanets scientists have measured so far tend to land somewhere close to Earth's density since they're built from similar ingredients: iron cores, rocky mantles, thin crusts. A rocky-sized planet landing noticeably below that expected range is unusual enough that it tends to grab a research team's full attention, because it usually means the planet's interior isn't simple solid rock all the way through. Something inside is either less dense than expected, arranged differently than expected, or actively behaving in a way that changes how tightly the material is packed together. For L9859d, that low density was the very first hint that this planet wasn't going to behave like a typical scaled-up version of Earth. When the team pointed JWST at L9859d and studied the starlight filtering through its atmosphere, they found something nobody expected: large amounts of hydrogen sulfide gas. If that name doesn't mean much to you, here's the plain version. Hydrogen sulfide is the exact gas responsible for the smell of rotten eggs. It's the same gas you might notice near certain hot springs, or in small amounts around some industrial sites here on Earth. It's a simple molecule made of just a couple of hydrogen atoms bonded to a sulfur atom, but finding a lot of it wrapped around a distant planet is not simple at all. Most of the time, when scientists picture a rocky planet's atmosphere, they're expecting things like carbon dioxide, water vapor, maybe methane, similar to the gases that make up parts of Earth's or Venus's air. Hydrogen sulfide in these amounts doesn't fit neatly into that picture. It's a strong signal that something unusual is happening far below the clouds, something actively feeding that gas up into the sky, rather than the gas just sitting there quietly from the planet's formation. Gases don't usually stay in an atmosphere forever on their own. Something has to keep replenishing them, or they'd eventually break down, escape into space, or get absorbed back into the planet. That's exactly what made the researchers dig deeper instead of writing this off as noise in the data or some kind of instrument error. A strange signal that keeps showing up consistently is usually the universe's way of saying, look closer, there's something real here. On Earth, hydrogen sulfide tends to show up in specific places, around volcanic vents, in certain hot springs, near some industrial and agricultural processes, and deep in oxygen-poor environments like swamps, the bottom of certain lakes. In every one of those cases, the gas is being actively produced by some ongoing chemical or biological process, not just sitting around left over from millions of years ago. Gases like this are reactive, meaning they tend to break down, get absorbed by rocks and water, or drift off into space over relatively short timescales, at least on a planetary scale. So detecting a large, steady amount of it in a planet's atmosphere isn't just interesting on its own, it's a clue that points toward an active source. Something on or in L9859d has to be continuously producing and releasing that gas to keep the levels in the atmosphere as high as the telescope observed them to be. That single idea, an active ongoing source rather than a one-time leftover, is what set the stage for everything the research team uncovered next. Here's the honest complication in this story. And it's a real one, not one we're inventing for drama. Scientists have two main boxes they usually put small, rocky-ish exoplanets into. One box is called a gas dwarf, a rocky core wrapped in a puffy blanket of hydrogen gas, kind of like a small rocky center with a thick, light atmosphere layered on top, similar in spirit to a miniature version of Neptune. The other box is a Hyson world, a term combining hydrogen and ocean, a planet with a deep, global ocean of liquid water, topped with a thick, hydrogen-rich atmosphere. L9859d doesn't fit cleanly into either box. It's not hydrogen-rich enough to be a simple gas dwarf. It's not showing the kind of water-soaked atmosphere you'd expect from a Hycean ocean world either. Instead, all the evidence was pointing toward something in between, something the existing categories weren't built to describe. Think about it like trying to sort a strange new animal into mammal or bird, and finding out it lays eggs like a bird but nurses its young like a mammal. Eventually, scientists just had to create a new category for animals like the platypus because forcing it into an existing box would have hidden more than it explained. That's the real tension here. Not an explosion or a countdown clock, but a genuine, we don't have a name for this yet moment in science. And when your data doesn't fit the boxes you've built, you either force it to fit and lose important detail, or you build a new box. The team studying L9859d chose the second option. This kind of moment actually happens more often in planetary science than people realize. For a long time, astronomers only had our own 8 solar system planets to use as reference points, so early classification systems were naturally built around those examples. Rocky and small like Earth or Mars, or gas giants and ice giants like Jupiter, Saturn, Uranus, and Neptune. But once telescopes started finding thousands of exoplanets, a strange gap started showing up in the data. Planets kept turning up in almost every size between small rocky world and gas giant, except for a narrow range right in the middle, sometimes called the radius valley. Scientists still don't fully agree on exactly why that gap exists, but it forced a whole new set of categories to be invented just to describe what was actually being found, categories that didn't exist when people were only looking at our own solar system. L98Ta59d is part of that same pattern. Another case where nature turned out to be more creative than our existing labels, and the labels had to catch up. This is the part of the story that earns the scientists wish wasn't real reaction. A team led by Harrison Nichols at the University of Oxford ran detailed computer simulations, essentially rewinding the clock on this planet's life across nearly 5 billion years. For comparison, that's roughly the same age as our entire solar system. Building a simulation like this means feeding in what we know about how planets form out of swirling clouds of gas and dust, how they cool down over time, and how gases move back and forth between a planet's molten interior and its atmosphere above. Then, instead of just trusting the model blindly, the team checked those simulated results against the real telescope data collected from L9859d to see if the model's predictions actually matched what Webb was seeing. What came out of that model was almost unsettling. L9859d appears to have a mantle made of molten silicate rock, essentially liquid stone, the same basic material that makes up much of Earth's interior, just kept in a liquid state instead of solid. And beneath that outer layer, the simulations point to a magma ocean that doesn't just sit in one spot, like a single lava lake or one active volcano. It appears to span the entire planet. Picture the whole world, not just one region or one hotspot, but the entire surface layer wrapped in a globe-spanning shell of liquid rock, glowing and shifting under an atmosphere that's constantly being fed by what's boiling up from below. And locked inside that magma ocean is a massive amount of sulfur, the same element that's leaking out as that rotten egg gas in the atmosphere above. The picture forming here is one of a planet where the surface breathes sulfur because underneath, an entire world's worth of molten rock is slowly cooking it out over billions of years in a cycle that's still going right now, today, while you're watching this. Not a one-time event in the ancient past, but an ongoing process, playing out on a planet 35 light years from where you're sitting.